Good morning, everyone, into the first of what I hope to be many episodes of Adventures in Spacetime. In this video expose, I and we will dive into a brief explanation of the life and works of one of the most well-known scientists of modern physics, Sir Isaac Newton. So sit back and enjoy the ride. First off, let's explore the history and works of Sir Isaac Newton. He was born on Christmas Day in 1642. He's generally regarded as one of the most original and influential theorists in the history of science and physics. His passion was to unite knowledge and belief to reconcile the book of nature and the book of scripture. He transformed the structure of physical science and physics with his three laws of motion and the law of universal gravitation, which he used to precisely predict the motion of stars and the planets around the sun. Without Newton and his discoveries, our modern world, as we know it today, would be vastly different. A brief history of his life, so to speak. He went to Cambridge University with the intention of obtaining a law degree, which by some accounts may be true, may not be true. Back then, physical science was not seen as influential, but rather a hobby, oddly enough. His instructions in Cambridge were dominated by the philosophies of Aristotle. However, Newton studied the philosophies of Descartes, Gassendi, Hobbes, and in particular, Boyle. He became interested in the mathematics, optics, physics, and astronomy. By the time he was 25 years old, which is by accounts, again, could be true, could not be true, based on every research that I've seen. He made several advances in said subjects of mathematics, optics, physics, and astronomy. Also, during this time, he began to think about gravity as to its function, its nature, and how it works in everyday life. Newton's greatest achievement was his works in physics and celestial mechanics, which culminated in his theories, the three laws of motion, and universal gravitation. By 1666, Newton had early theoretical inquiries of the three laws of motion. Using his discoveries in optics, he constructed the first real telescope, the reflecting telescope, which is vastly superior to Galileo's. Newton found that the isolated facts and laws of science at the time were capable of describing some phenomena but predicting only a few, which in turn means sorely lacking in real world applications, which his development of a system of laws could be applied to an enormous range of physical phenomena and theoretical thought experiments. And he used them to make exact predictions to a wide variety of subjects. With Newton, his works in two books, namely Optics and Principia, the latter of which was widely regarded as one of, if not the greatest scientific book ever written, which marks at the beginning of modern day theoretical physics as a mathematical field that we know of today. In 1667, Newton returned to Cambridge after some time of hiatus. 2 years later, he was appointed second Lucasian professor of mathematics. As a side note, a position that was held by Stephen Hawking for 30 years until his retirement in 2009. Later in life, once he achieved wealth and success in his particular field of what can be classified as theoretical physics, he, as both a public figure and servant of the state, he became an attraction sought out by both the intellectual tourist and the curious layman, in a way previously inconceivable at the time. When he was a Cambridge Don, in today's terminology would be a tenured professor, or perhaps a president of the university. He was incapable of holding an audience for long periods of time with his lectures, since, like some professors, they tend to ramble on and on and on and never get to the point till later on. By the 1700s, he was the dominant figure in British and European sciences, a feat never before seen until the modern era. In 1705, he was knighted, the first and not the last scientist to be honored for his work. When Isaac Newton died in March 20th, 1727, at the age of 84, he was buried in Westminster Abbey, the first scientist to be accorded this honor, which at the time and even today is a very prestigious high honor. He has been regarded for almost 300 years as the founding exemplar of modern day physics. In essence, Isaac Newton, by a wide variety of scientific colleagues at the time and all the way to the present day, including laymen, curious folk, and whatnot, he's considered to be one of the fathers and creators of modern day theoretical physics, which all started with his three laws of motion, which at the time was revolutionary. Even today, they are still being used. His equations are used every day for just about every application that we can perceive. And also, his theory of universal gravitation is still widely used today as well for a wide variety of subjects until Albert Einstein came along with his theory of general and special relativities. Even then, Newton's law of universal gravitation is still being used. And now for the part we've all been waiting for, Newton's law of motion and universal gravitation. His first law states that every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by action of external force. Layman's terms, it is every object will remain at a particular state where it is at a relaxed position, either at rest or in perpetual motion in a straight line, until acted upon by an external source, like a windmill going around in a wind until another burst of wind turns it, or a ball is sitting still at rest until someone kicks it and it rolls around, even up to living beings who want to keep moving in a single line until they decide to turn around, even vehicles. These three laws, particularly the first law of motion, is used for every single aspect. Now, there is no true formula for his first law, since his first law of motion is considered to be theoretical. But I did come up with a diagram based on several researches that I have done this week. And I apologize in advance for my handwriting and whatnot. I'm not exactly the best writer or best drawer. But here we go. When forces are balanced, objects will remain at rest with, I'll just abbreviate objects at rest as OAR for simplicity. Which is described by using a simple formula. Velocity is equal to 0 meters per second. And as it is accelerated. The acceleration is 0 meters per second squared. This basically means as long as it's not moving, it will remain unchanged. And it will stay at rest. I know my handwriting sucks, but now, as for objects in perpetual motion, which I'll call OIM for objects in motion, which is described as velocity not equal to 0 meters per second, which is as long as if there's acceleration or external force, will be acceleration equals 0 meters per second squared, which will stay in motion. Stay in motion, same speed and direction. I know my handwriting sucks, but what can you do? Or there is one formula that I did see. It's kind of related, but it does describe some of it, which is the sigma of force equals 0, which is d velocity divided by dt, which is object velocity divided by object in time, is equal to 0. which is by its own account pretty self-explanatory. If something is at rest, it will want to stay at rest until external force is exerted on it. Something in motion, it will want to stay in motion until external forces are acted upon it. Now, as I said, I'm going through a brief description of everything. Later on in future episodes, as I go through various theories, I actually go through each one of his three theories of motion in more detail. But that won't be till later on. Now, Newton's second law defines a force to be equal to the change in momentum which enhances in time. Which is described as let me think about it here. Momentum is defined by mass, which is m, of an object times its velocity, which is represented by v. Now, time, represented by t. X is the location of the object. M is for its mass. And v for velocity. Which will, in essence, become, well, not in essence, this is actually the only true formulae for the second law of motion. What it states is that you can use these equations of mass, velocity, and time to measure the force required to move an object, either from a resting position or a moving position. So, here's how the formula works. Difference, force, equals mass to the single power times velocity to the single power minus m0 v0 divided by time divided by time 0, which is the force required to move an object is equal to its mass and its velocity while moving minus the mass and velocity of it at rest divided by the time beginning and the time ending. Which then there's constant mass, which states that when an object is in motion, it has the same amount of mass, more or less, which is derived into this equation. Force is equal to the mass times the velocity divided by the time. And both those equations will formulate into an equation that we all know from middle school, which is force is equal to mass times acceleration. Now, there is a practical application to this that can be used in everyday life. One of which is using vehicle, person walking. In this example, I'll use a jet. I apologize in advance. And that's actually the best draw in the world. So, here we go. The jet. Now, you would use these equations of mass, velocity, and time to measure the force required to move an object, which is x is the object, velocity, and mass of it moving, versus rest, which equals to the force required to move an object from rest to motion, and vice versa. Which would be translated. Now, you can substitute x for d, so both of which are interchangeable for object in both equations I've found, which is the force is equal to the object of velocity divided by object of time, which translates to object times mass and velocity divided by object's time. The constant factor is force is equal to the mass of the body, and A, which I forgot, is acceleration. Sorry about that. And the constant for it is the force is equal to the mass times object's velocity over the object's time equal to mass times acceleration, which brings you full circle, which is what's required to move an object from rest to motion, and also to require a motion object to change its acceleration from 0 to moving, or moving to 0, or moving it from a straight line via external source. Hope everyone can see that. Now, Newton's third law, which is widely used in today's day and age for just about everything, which I'm sure everyone knows, when an object is at rest, and when it wants to stay at rest, or object in motion, it will stay in motion. And also, no, that's not it. Sorry. When one body exerts a force on the second body simultaneously exerts force equal to magnitude of the opposing object's force, which is, I'm sure everyone knows, equal and opposite reaction. Which, again, F is force. No, not Luke, use the force. Where that force of object A times object B is equivalent to the negative force of B and A. So, when you have one object applying force to another object, it is equal and opposite of the reaction of vice versa, which we all know from middle school. Say, for example, I push a box. I want to push it that way. Now, according to this reasoning, the box, say, for example, push it 2 newtons, which is just a poke. Now, according to mathematics, the box should exert the same amount, right? Wrong. That's a very common mistake made by people who really don't understand the equations, which is understandable. It is kind of tricky to understand. But what that shows is that if you apply pressure to an object to force it to change from rest to motion, the object theoretically pushes back at you. But since you have more force behind it, the reactionary force is negligible. So, in essence, if you exert, say, 2 newtons of force on an object, then it is theorized that the object produces 2 newtons of counterforce on you. However, in reality, it doesn't look like that since the object may be smaller than you, so its reactionary force would be negligible at best. However, if the force you're trying to exert on something as heavy as you, or heavier, same amount of mass, the same amount of mass as you, the same amount of acceleration, then theoretically it will cancel each other out, but the law still remains. Then, moving on to Newton's law of universal gravitation. That extends beyond Earth, beyond where we're at right now. It's also called universality of gravity. All objects attract each other via gravity, which later on Einstein shows that gravity is actually a curvature in space-time. But that's a later subject. We're dealing with Newtonian physics at the moment. Newton's conclusion is that the magnitude of gravitational forces is summarized symbolically as force of gravity is proportional to the mass of object 1 plus mass of object 2 divided by distance squared. You can use this formula, invented, which is F is force, grav is gravity, M1 is mass of object 1, M2 is mass of object 2, and the distance is d is the distance of the object's center of mass from center line to center line of each object, as it is either pulled closer to each other or repelled against each other. In layman's terms, as I like to understand it, the force of gravity is proportional to the combined masses of objects 1 and 2 divided by distance squared. Everything that we know today is based on Newtonian physics, which was created by Sir Isaac Newton. His works of the 3 laws of motion and law of universal gravitation, without which our world would be vastly different. We would have no understanding of anything as we do today. Hence, new Newtonian physics, no Einstein, no Stephen Hawking, and so on and so on. Excuse me. Now, since we know everything, since we do have understanding of Newtonian physics, again, all of these equations from Three Laws of Motion and Universal Gravitation, along with all the other works that he's done, which I didn't have time to cover today. But as I said previously, later on, when we go through individual series themselves, we actually explore those. I hope everyone enjoyed my video expose of Isaac Newton and a brief description of his laws of three laws of motion and universal gravitation. His works can be found in primarily the Principia Mathematica, which I would suggest you try to find either in a library or online and try to browse through it best you can. It'll give you a better understanding of what universal gravitational fields are, three laws of motion. There's a website called Physics Class, I believe, where they use various studies of science, and break it down into areas where students can understand it and laymen can understand it. I suggest you looking that up too. That's where I got some of my information at, along with Britannica and historical biographies. Now, this concludes this week's episode. Next week, I plan on doing another great, hopefully next time I do a better job, of Albert Einstein and his various theories, particularly the theory of general and special relativity. Go down and hit the like button if you like it. Post some comments below whether you liked it, what you would have changed, what you would have said, what you suggest. Until then, adios. Oh, and science is only as fun as you allow it. The enemy of science and knowledge is ignorance. So, keep learning, everybody. There's no substitute for it. Thank you, and see you next time.